So just one reminder that homework 2 is due tonight. Okay, many of you guys have finished your homework 2 already. Still a couple of you guys haven't finished them, but you have almost. I see you guys are almost done. Okay, so that's very good. So last time we talked about the to describe an object, we need certain quantities. So the first a few quantities we learn is position, displacement, and velocity. Okay, so for the position, you need a reference or frame of reference. So then once that is chosen, then you can refer to that reference to describe your position. You can say certain like distance away, and then when you have the object that is moving, then you can say the change in position, which will be described by displacement. Okay, the difference between these two quantities is position is a scalar quantity. Okay, and then displacement is a vector. Now in physics, later on we'll see that sometimes we refer position as position vector. Okay, as well. So in that case, then you have a particular position of the object. Okay, so then what you wanted to, let me just mute you guys all to reduce any background noise. Okay, you can unmute yourself if you want to speak. So then that is just a technique that people will be using to better utilize like the position. So then you can do the difference of the position vectors to get the displacement. In that way, it's just a technique. Okay, but position can be considered as the scalar. Okay, unless you say this is a position vector, then you mean that this vector starts from the origin of your coordinate system and then points to the position where the object is. Okay, that's the position vector. So for displacement, then it's the change in position. So you do final position minus initial position. Okay. So if you have two positions of the object, say initial and final positions, then you can determine what's the distance between the two positions. Okay, or the distance traveled. So these two terms or these two quantities, many times they are different if your the object travels in a journey that has multiple parts. Okay, meaning it turns direction when it's moving. Okay, so then they are different. Okay, if the object doesn't turn direction as it moves, then distance and distance travel will be the same. All right. We also talk about velocity, so that is defined as displacement divided by time elapsed. So this is a vector quantity. Okay. Now average velocity is defined as distance traveled or distance divided by time t. So these two quantities, the average speed, although we say speed is the magnitude of the velocity, but average speed is not necessarily the magnitude of average velocity, because if the object, when the object is moving, if it turns direction, then these two are, the average speed is not the magnitude of average velocity. Okay, so just to be clear, just want to clarify this. Okay, so when we are talking about average speed, so this is like average speed will be different, okay, than the magnitude of average velocity if the object actually turns direction when it's moving. Okay, it turns direction in the middle of the movement. All right. We can do graphical representation of the motion of an object. Okay, so you can plot the position versus time t. Then you can get the velocity information from this plot. Basically, you are taking the slope of the position versus time t graph. Then you'll get your slope. Okay, which is identical, which happens to the same as the definition of the velocity. Okay, so then slope from a position versus time graph gives you velocity of the object. Okay. So And then we also talk about instantaneous velocity and speed. So this could be a varying quantity. Okay, so instantaneous velocity could be changing all the time. All right, so although you have an average velocity for a certain like journey of an object, but this velocity could be changing. Okay, um, not only the magnitude or speed, but also the direction of the velocity could be changing. Okay, and also the speed could be changing all the time. Now for instantaneous velocity, you do derivative of the position with respect to time t, all right? While if you are doing average velocity, you do change in position divided by time t, okay? The difference is here, so it's change in time, change in position over change in time, that gives you average velocity, meaning you are doing final position minus initial position divided by the time it takes, okay? On the other hand, for instantaneous velocity, you do time derivative of the position, and then at that particular time instance, you plug in the time into your expression for velocity, then you'll get your instantaneous velocity in that way. Okay, and the instantaneous speed then will be the absolute value or the magnitude of the velocity. Okay, of the instantaneous velocity, you just take the absolute value of it. Okay. So instantaneous speed, then it's when you take delta t goes to 0. So this is derivative of the x with respect to t, okay? And then it's just a magnitude because we are talking about the speed, which is scalar form, all right? So then if you have a plot of the position of the object versus time t, you can solve for the instantaneous speed of velocity at any point. Okay, so just doing the tangent line on the curve at that given moment, then solve for the slope of it. Okay, otherwise, if you are looking for average velocity, then you pick two time intervals, you connect the two points from the curve and then solve for the slope. Okay, you will get the average velocity. All right, so today we are going to talk about average and the instantaneous oscillation. Okay, so as many times the velocity or the instantaneous velocity will be changing, so then that means the velocity is not always constant. Okay, so you might have changing of velocity from one moment to another moment. So say your initial and final velocity are different, then you can calculate the average velocity given in these two time instance, the final and initial. Okay, so you do change in velocity divided by change in time t, which means final velocity minus initial velocity divided by final time minus initial time. Okay, as you can see, because velocity is a vector, so then oscillation or average oscillation is a vector. Okay, so in general, oscillation should be a vector. The SI unit for oscillation should be meters over second square. Okay, because for velocity it's meters over second, and then divide by time, which is in second. So then you should have second square in the denominator. Okay. The table here lists some of the common oscillations, their magnitudes here. Oscillation of gravity, which we'll encounter a lot in this class, will be 9.81 meters per second square. Okay, so this I think this is the only number you probably want to memorize here out of this table. Okay, 9.81. Okay, so so let's see. So when we when we just introduce the average oscillation in the previous slides, we say there's change in oscillation, right? Now, the term oscillation might imply that the object is speeding up, right? Because it says oscillating, okay? But actually in physics, okay, when we just say change in velocity, so that means your velocity could be, or the speed could be slowing down, right? So then in that case, the object should still have oscillation because there's change in velocity, right? So in that case, some people may refer to as if the speed goes down, then it refers to as deceleration. But both cases of if the object is accelerating or decelerating, then we say the object has acceleration. Okay. So when deceleration happens, then the velocity and acceleration, they are in the opposite direction. So one goes in that way, one goes that way. Okay. So then the velocity is slowed down. Okay. But just keep in mind when we are talking about decelerating of an object, then it has an acceleration as well, just because the acceleration is in the opposite direction of the velocity. Okay. All right. So several scenarios here to consider. If the velocity and acceleration are in the same direction, then the speed will go up. Okay. So otherwise, so in the figure A and D here, in both scenarios, velocity and acceleration are in the same direction. Okay. In scenario B and C, in both cases, velocity and acceleration, they are in the opposite direction. So in these two cases, the car, its speed will decrease. Okay. So because acceleration and velocity are not in the same direction. Okay. All right. So let's take a look the first exercise problem here. So a particle, it says a particle has an acceleration of 6.24 meters per second squared for 0.450 seconds. At the end of this time, the particle's velocity is 9.31 meters per second. What was the particle's initial velocity? Okay, so in this chapter, we'll be just talking about one-dimensional motion. Okay, so unless otherwise specified, then the object will just moving along one direction, either going in the positive direction or turns direction in the negative direction. Okay, so if you see numbers that is positive, that means it's having direction in the positive direction. Okay, so acceleration is positive, final velocity is positive as well. Okay, now I will have you guys try to solve for this one, and then we can take a look on the solution just in a few minutes. Okay, I think probably maybe 3 minutes should be enough. Okay, it's a simple one. It's just the acceleration. You will use the acceleration equal to final velocity minus initial velocity divided by time t. Okay. All right, so it looks like most of you guys have your answers submitted here already. I do see the correct answers there. So for most of you guys, you got this one right, okay? So we can take a quick look on here. Let me stop sharing here so you guys can see um, my work on the paper here. So we are going to use the definition for the oscillation, average oscillation, okay? So I'm going to just say A. I don't want to do A sub AV, okay? But if you can do that, okay? So on this one, I'm going to just do, because it's defined as change in velocity divided by t, okay, or delta t if you want. So change in velocity means final minus initial, okay? So we know that A is given, right? It's 6.24 meters per second square. The final velocity is given 9.31 meters per second. T is 0.450 seconds, okay? So then the three quantities here are given, only one is unknown in the equation here. We can solve for this unknown, okay? So just the algebra here, you want to multiply both sides by t, okay? So then AT equals to here, we get rid of t from the right hand side, equals to V final minus V initial, okay? So then V initial is going to be equal to V final minus AT, okay? I'm skipping just a couple steps here, but quick step, you guys should be able to figure that out, okay? So then this is the final minus oscillation 6.24 meters per second squared multiply 0.450 second, okay? So this will tell you 6.502 meters per second, okay? And 3 sig fixed to keep, so 6.50 meters per second, okay? So that's your final answer. And then most of you guys got this one right, okay? Which is great here, okay? Let me know if you have questions, okay? Just unmute yourself and then you should be able to speak up. All right. So if you guys are clear, we can move on here onto the next one here. So we just talked about the average oscillation, which means you are doing change in velocity divided by change in time t, all right? So then similarly to instantaneous velocity, if you are looking for instantaneous oscillation, you'll be doing time derivative of your velocity in this case, okay? So you'll be doing d dt v, okay, as a function of time t. All right. So we can also do graphical representation. Okay. So if you have a plot of velocity versus time t, then you can get instantaneous velocity oscillation at any time. Okay. So for example, t0 here, you can take a slope of that curve or the tangent line of that curve and then solve for the slope of it. Okay. And also for the if you have a different curve, like on the right hand side here, you can do the same, okay? You can do tangent of the line, then slope of the line, the tangent line will give you instantaneous oscillation. Otherwise, if you are looking at two time intervals, two time instance, then you will get the average slope of it or the average oscillation of it, okay? All right. So another example here, say if you have a velocity that is versus time t that is a linear, so that means you will only have a single slope throughout the motion of the object, right? So that means the oscillation of the object is not changing. So then you have a constant oscillation, okay? So then for the oscillation versus time t plot, you will have a flat line over there, okay? So this then refers to a constant oscillation motion, all right? If you have a curve like this, this looks like a hyperbola, okay? So then this is a plot of a quadratical equation, okay? You'll have, in this case, then you can take the tangent line at many time instance, then you can replot and then solve for the slope of the tangent lines, and then you can replot the slope versus time t, which is the oscillation versus time t. Okay, so in this case, it'll give you a linear as the oscillation. So then oscillation is changing here. Okay, so it goes from 20, decreases down, and then reverse direction, and then increases up again in the opposite direction. Okay, so this is the example in 3.6 in the textbook. You guys can see the details of it. Okay, now let's have exercise the oscillation. Like if you have a plot of velocity versus time t, how would you get the oscillation versus t? Okay, so let's take a look at this one. I think let's do this together. Okay, so I'm going to stop sharing, and then you can see my work on the paper here more clearly. Okay, so again, if you look at the plot here of v versus t, you can see there's several parts like consist. Oh, hi, I'm finally back. Yeah, I had a quite great deal of trouble with my internet. Couldn't get resolved, but finally we are back. Thank you for staying. Okay, so let's see. So let's get back to where we were. We were about to get the information about the oscillation versus time t from the velocity versus t graph. Okay, so that's where we left with. So so we're going to just do like the different parts on the figure. Let me show my paper here. So the first linear part goes from the 0 second to 20 second from the graph. Okay, so you're going to just say you're going to solve for the oscillation for the first part from 0 to 20 second. You take the difference in the velocity, so it goes from 6 minus 0, that's the final velocity minus initial velocity, divided by the time. Okay, so 20 minus 0. Okay, so which will give you about 0.3 meters per second square on the first part. Okay, so then you can start with your plot of oscillation versus time t. All right, from 0 to 20 seconds, then you're going to just indicate this is 0.3 meters per second square on that first part. Okay, the second linear part on the plot so goes from 20 second to let me check 50 second. Okay, so at the bottom here for time, you're going to do 20 minus 20 or 50 minus 20, and then the final velocity at that time moment was from 2 minus 6. Okay, so this then will give you roughly minus 0.133 meters per second square. Okay, so then you're going to indicate, and this is 20, so 250 somewhere about there, minus 0.133 meters per second square. Okay, so etc. And the third line is a flat line. That means your oscillation is 0, because then the change in velocity is the same. There's no change in velocity. So from 50 to 70, okay, 50 to 70. So this is 0 meters per second square. Okay, and then you can do the same from 70 to 90. All right, you'll be doing the on this one will be 4 minus, so you'll be the 4 minus the initial will be 2, okay, divided by 90 minus 70. Okay, so that will give you roughly about 0.1 meters per second square. Okay, so you're going to indicate, okay, this is about 0.1 on this time instance, 0.1 meters per second square. Okay, and then from 90 to 100, okay, you'll do the same. Will be negative 2 minus the initial of 4 divided by, for the time difference, is going to be 100 minus 90. Okay, so minus 0.6 there. Okay, so then somehow relative large here. Okay, so indicating that minus 0.6 meters per second square. Okay, all right. So that's roughly what you have. Okay, of course I'm doing this in a very like rough scale here. I don't have a ruler with me for right now, but if you can do with a ruler and with the proper scale, that will look much better. Okay. All right. Any questions you guys might have?
Excuse me, Dr. Howe.
Yes, go ahead.
Can you explain the section between, so you have the 20 to negative 0.133, and then is that a line along the t-axis?
Between 50 and 70?
Yes, looks like it.
Right, yeah. It's because oscillation between those two time instants is 0. So yeah, you indicate there's a line there. Yeah, that's right. Yeah, we want
Okay,
to
thank you.
indicate that way. You're welcome. All right. So let's move on here. So then we have checked the position or displacement, velocity, and oscillation. Okay, so these are the quantities you can use to describe the motion of an object. Okay, so let's combine up all of this. Okay, or let's look at them together and then see what in general we would have out of all these quantities. Okay, so to do that, we are going to just check on the simple case if you have constant oscillation. So that means oscillation throughout the motion of the object is not changing. Okay, so A is being A is not changing, A is constant. Now let's simplify some of the notation here. So when we talk about change in time t, we are going to simply just use t. All right. So then when we look at all the equations we have learned so far, we don't have to write all of them. Now delta x simply refers as x final minus x initial. So we are going to drop the subscript here of final. So x simply means the final position, okay, instead of f x sub f. Okay, we are dropping the f subscript here. Similarly for velocity, we are going to drop the f, v sub f. Okay, so then v is the final velocity minus v0. Okay, and then constant oscillation here, so then average oscillation should be equal to just oscillation. Okay, just use one symbol, oscillation, for that. Okay, so after we simplify these notations, let's look at the let me put this in presentation mode. Let's look at the first thing we learned about was the velocity, average velocity. Okay, it's not the first thing, but one of the earlier quantity we talked about to describe motion. So average velocity was defined as change in position over time t, which means x final. Now we are dropping the sub f, so x minus x0, which means initial, divided by time t. Okay, delta t becomes t, now just simply t. Now, if we rearrange this equation, we multiply the left side of equation by t and then the right side equation by t. So then we have v times t is going to equal to x minus x0. Okay, and then if we rearrange the terms, so move x naught to the other side of the equation. So then on the left hand side, you have x naught plus v average times t equals to x, right? So then you flip the two sides, you'll get the final position is equal to initial position plus average velocity times t, or average speed times t. Okay, so either way. So this is the equation 310 in the textbook. Okay, now keep in mind in this expression over here, when you have v with a bar, so that means it's average velocity. Okay, so this is average velocity because that's a definition. Now I think earlier we used v sub av. Okay, but you can simplify this notation by just using v with a bar, okay, that indicate this is the average velocity. So now I want you guys to pay attention to this term v with the bar average velocity, okay. So a common mistake to make here is take this as final velocity, okay. So sometimes people just think this is the final velocity and then plug in the number of for final velocity here, then you'll get a wrong answer for the x, okay. So this average velocity is equal to, if this is constant oscillation is not changing, so it's equal to 1/2 of the initial plus final, okay. Should be 1/2 of initial plus final, all right. So now these are the first two equations that you guys will use often when you are solving for a one-dimensional problem. All right. So so in this case, so we are talking about constant oscillation, right? So that means the change of the velocity should be linear, okay? So velocity versus time t should be linear, okay? So in this case, and then you can only use the equation of 1/2 v0 plus v if this is constant oscillation, okay? Otherwise, if the oscillation is not constant, so that means changing in velocity is not homogeneously throughout the journey, then it's not, you cannot use this expression to calculate for the average velocity, okay. So just keep in mind, to calculate average velocity using this expression of 1/2 initial plus final, that applies only when you have oscillation that is constant, okay. Otherwise that doesn't apply, okay. All right, now let's take a look on the definition of initial for the oscillation. So oscillation is defined as delta v over t. So then v final minus v initial gives you delta v, okay, divided by t. So in that sense, we can do the same as what we did from the definition of v equals to delta x over t. So up to a couple rearrange of the terms. So multiply left hand side by t and then right hand side by t, and then rearrange the terms. You'll arrive at this expression. Okay, so v equals to v0 plus at. Okay, so that means final velocity is equal to initial velocity plus oscillation times t. Okay, the time it takes. Okay, so then this is the third equation. All right. So then I think, yeah, so the detailed derivation of this is in the textbook, okay. You can, if you didn't catch anything, you can go back to the textbook and then check on the derivation, okay. So the next equation we are going to derive are based on the ones we have seen in the previous couple of slides. So for this one, this is from the previous slide, okay. We just derived that one, or we check on that one moments ago. And then the average velocity should be 1/2 of initial plus final, okay. So this is again assuming constant oscillation. So then if we look at these two equations, you take the final velocity in the 3.11 here, okay, replacing the v with this expression because final v is equal to initial v plus at. So then average will be equal to 1/2 v initial plus at, okay. So v initial plus at, that's the final, the v, okay. And then again with the first equation of the 310 we checked earlier, combine that with this guy, all right, you are going to arrive at this 3.13, okay. So I'm going to show you the steps missing from these two equations to this one, okay. So basically, you will be replacing the V average in 310 with this long expression. Okay, so then let me put my Okay, you guys can put my video in speaker view, so then this can be clearly see, okay? Or just wait a minute or one moment before I stop sharing. Let me just copy this one down here. So x final equals to, this is from 310, x naught plus v average. I'm going to take the expression above it, 1/2 v0 plus v0 plus at. Okay, this is the v average times t. Okay, so let me stop sharing for just right now. Now you can see here v0 plus v0, this will give you 2v0, okay, plus at from the parentheses. Then you will be distributing 1/2 into the parentheses, the two terms in the parentheses, and also the t into those two terms as well, okay? So then the first term here, you just copy it down, plus 1/2 times v0, right? And then times t plus 1/2 again, at times t. All right, so the 1/2 and 2 will cancel out. Then this is going to be equal to x naught plus v naught times t plus 1/2 a t to the second. Okay, so this is your x. So this is the 310 or 313. Okay, this is the equation 3.13 in the PowerPoint slide. Okay, all right. Now I'm going to show you the last equations that you would need for one-dimensional motion. So basically, you can use 5 equations for one-dimensional motions. Okay, use any of them, or maybe 2 of them, or maybe 3 of them. Sometimes, but nothing besides these 5 equations. Okay, so the last one will be the 314 listed on the slides at the bottom here. So again, it's derived from 312 and 311 here to start with. Okay, so from 312 you can rewrite. So then you can write t in terms of the other quantities. Okay, so basically you are going to do v minus v0 on this side, or move this guy, the v0, to the left hand. Okay, and then you will have at remaining on the right hand. Then you divide both sides by a, you'll have just t on the right hand. So t is equal to v minus v0 divided by a. Okay. Now from 311 here, v average is equal to 1/2 v0 plus v. Okay. So then you are going to take these two expressions and then plug in those v bar and then t in 310 here. Okay, then you'll get to 314. So let me just show you how to get that. So you'll now in 310, this is x equal to x naught plus the v average. Now you're going to take 1/2 v0 plus v. Okay, that's v average, and then t, you are going to use the v minus v0 divided by a. All right, so this is v average, this is t. Okay, you can rewrite this guy. You can do, so I'm going to just put the 1/2 in front. Okay, and then I have v plus v0. All right, and then I'm going to take the a in the front. So that means 1/2a. Okay, and then v minus v0. Okay, now if you have v plus v0 multiply v minus v0, that will give you v squared minus v0 squared, right? And then 1/2a in front plus x naught equals 2. Just take x down. Okay, so then now you can move this guy to the other side of the equation. You can say now x minus x naught equals to 1/2a v minus, or v squared minus v0 squared. Okay, and then multiply both sides by 2a. Get rid of 2a there. All right, so then you'll have v squared minus v0 there. Now plus add 2 v0 squared to both sides of the equation. Okay, So then you'll have v0 squared plus 2a x minus x naught equals to v squared. Okay, so this is basically equation 314. Okay, you kind of just put the v squared on the right hand side, left hand side, and then this expression on the right hand side. Okay, so this is how this equation is being obtained. Okay, so to summarize, so these are the equations you will need, the 5 equations you will need, okay, for one-dimensional constant oscillation motion. So for any problems with constant oscillation and one dimension, you can use combination of these equations, okay, either one of them or two of them, and sometimes maybe 3, okay, but nothing else than these ones, okay. So as we run out of time, I think we are going to stop here for today. Again, I apologize that my internet had issue earlier, but we can look at the examples tomorrow, okay, in the class, okay. All right, so I'll see you guys tomorrow then.